So this is a presentation about statistical thermodynamics of surface-bounded exospheres by Norbert Schöckhofer. And I will present abstract theory, but it has a very specific motivation and very specific applications. So the motivation is that a water exosphere has a capability to transport water molecules from any locations on the moon to the cold traps. And the theory, which goes back to 1961, says that these molecules hop repeatedly on ballistic trajectories with thermal velocities. So there is evidence for a water exosphere on a moon, but we still don't know whether this theory actually works or not. And so it's a good working hypothesis. And what I am trying to do here is advance that theory in anticipation of additional measurements in the near future. And the first topic I'm after, or issue I'm after, is the vertical density profile of such an exosphere. So you have an ensemble of ballistic trajectories, and all we need is really the launch velocities, and we can calculate the density profile. And the theory is that most molecules, not necessarily all, but most molecules should thermally accommodate. I mean, even at the speed of light, the time it takes them to transverse their own diameter or molecule is still longer than the vibrations in a solid which we touch. And so we do pick up that temperature. And then with thermal desorption or thermal accommodation, it will leave at a random direction. And if that happens, then what results is a Knudsen cosine law. It's also been known for a long time. And there is this extra factor of cosine theta or VC for the probability distribution of a vertical component of velocity. So the colored equation at the bottom is a probability distribution of velocities. And X and Y components are just Boltzmann factors, and the C component has this extra factor of VC because we are on a wall. So this is exactly the same as an ideal gas with a maximal Boltzmann distribution as experienced by a wall. But it's derived, it can be derived irrespective of whether there actually are collisions in that gas or not, through this Knudsen cosine law and thermal desorption. And so then one can just calculate the density profile. But let me make another theoretical point here, is that the temperature of the exosphere is actually exactly the temperature of the surface, because by the very concept of temperature, the zeroth law of thermodynamics, an ensemble of trajectories in equilibrium with a reservoir at a certain temperature must have the same temperature. And I pointed out, because the literature is full of discussion about how, with ballistic trajectories, velocity distribution changes, and therefore how would one define temperature? But there is actually this straightforward, simple, precise way of defining the temperature of an exosphere. And well, let me go on to the results for the vertical density profile, which one can calculate analytically for the velocity distribution I showed. So for a horizontal thermal surface, it's just this the blue graph, which is an exponential. So this is collisionless, but it's still an exponential. But if one does this from a vertical wall, right? So if I go back to velocity distribution here, now the x component doesn't have this factor VC, which the c component has. And so for a vertical wall, one gets a different density profile, and one which diverges logarithmically near the surface. So this sort of looks like it's made up of two populations with two different temperatures, but it's actually a single population, or a population with a single temperature. And so from a rough surface, we have horizontal and vertical components, so it would be a superposition of these two profiles, and the divergence will survive. So the expectation is that the roughness leads to a ground-hugging population. Now, another application is in the context of cold traps. Cold traps are areas cold enough so the sublimation rate is negligible, like a meter per billion years at 120 Kelvin or so. But more precisely, they're really places where a temperature of a sublimation loss is less than what's supplied over long term. And the long term, maybe a billion years. So the long term, from a long term perspective, it actually is a balanced equilibrium because what's steady lost and what's episodically provided. So there's this equation, the Hertz-Knudsen formula, which provides a sublimation rate of ice into vacuum, which is a function of a saturation vapor pressure, which sort of encodes the energy barrier a molecule has to overcome to leave a surface. And so one can plot sublimation rates on this. There's a phase diagram of water. One can plot sublimation rates onto the ice vapor line. 1 meter per billion years would be at about 110, 115 Kelvin. But it can also be viewed, at least approximately, as the long-term average of the pressure of the exosphere, because the pressure of the exosphere gives us the supply rate. So an application of that is is ice caves on the moon, a possibility we are pondering about now. So there are almost certainly caves on the moon. Now, is there ice in some of them? It's certainly cold enough, but it's also very dry. So this argument suggests that ice in the cave will be gradually lost if the interior of that cave is at a temperature of 120 Kelvin. So it sort of gives us a geographic limit to the extent of potential ice caves on the moon. And here's a summary, but I'm out of time, so I just leave up this summary.